All right, let's dive in. For the next few minutes, think of us as cosmic detectives. When you look up at that vast night sky, you're seeing countless stars, some of them trillions upon trillions of kilometers away. So how on earth do we know anything about them? That's the mystery we're cracking today.
I mean, it's a fantastic question, right? We can't go visit a star. We definitely can't take a sample. The only thing we have, the single clue that makes that incredible journey across space to reach our telescopes, is its light. And it turns out that light is telling a story, and we've gotten really, really good at reading it.
So, our investigation begins by treating starlight not just as a little twinkle, but as a detailed message, a whole universe of clues just packed inside, waiting for us to unpack it.
And here are the three big secrets we can pull from that light. First, a star's luminosity. That's how bright it really is. Second, its temperature. You know, how hot it's burning. And third, its mass, how much actual stuff it's made of. Get these three things, and you've got the fundamentals that define a star's entire existence.
Okay, so how do we do it? How do we actually decode these properties from just a beam of light? Let's take them one by one, starting with a star's true brightness.
First things first, we got to get one thing straight. A star's true brightness, its luminosity, is kind of like the wattage on a light bulb. It's a fixed number. But how bright that bulb looks to you? Well, that completely depends on how far away you are. It's the exact same with stars. So to figure out their true wattage, we first need to solve for that one missing variable: distance.
And astronomers have this brilliant trick for doing just that. It's called stellar parallax. You can actually try yourself. Just hold your thumb out at arm's length, close one eye, then switch to the other. See how your thumb seems to jump against the background? Stars do the same thing, but instead of us blinking, we use the Earth's entire orbit around the sun.
So here's the game plan. We take a picture of a star, then we just wait. We wait 6 months for the Earth to travel all the way to the other side of the sun, and we take another picture. That nearby star will look like it's shifted just a tiny bit against the super distant background stars. And by measuring that little angle, a bit of simple geometry gives us its distance. It's incredible. One property down.
All right, on to property number 2, temperature. And for this one, the clue is surprisingly simple. It's the star's color. Yeah, that's it. Just think about a piece of metal in a forge. It glows red, then orange, then white hot as it heats up. A star's color tells us its surface temperature in the exact same way.
Now, to get more precise, astronomers spread that starlight out into a rainbow, what we call a spectrum. And woven into that spectrum are these unique dark lines, like a fingerprint, that reveal its exact temperature and chemical makeup. This gives us its spectral type. The whole sequence goes O, B, A, F, G, K, M, from the hottest blue stars to the coolest red ones. And yep, the classic way to remember it is O, B, a fine girl kiss me. Our sun, by the way, is a G-type star. Pretty average.
And finally, how do you weigh something you can't possibly put on a scale? This one's my favorite. The secret, and it's a big one, is that we can only directly measure a star's mass if it's not flying solo. It has to have a partner.
Turns out, about half of all the stars you see are in these binary systems, gravitationally locked in a dance with each other. And by watching that cosmic dance, measuring how long their orbit takes and how far apart they are, we can use Newton's laws of gravity to calculate their mass. It's an absolutely mind-blowing technique.
Okay, so we did it. We've gathered our 3 key clues for thousands and thousands of stars. We have their true brightness, their temperature, and their mass. The detective work is done. The next step is to lay out all the evidence and see if there are any patterns.
And this is where the magic happens. What do you think you'd get if you took all this data and threw it onto a single graph? Would it just be a random, meaningless mess of dots all over the place?
Not even close. You get this, the Hertzsprung-Russell diagram, or the HR diagram for short. And this is, without a doubt, one of the most important graphs in all of science. It plots a star's true brightness against its temperature, and you can see the stars don't just fall anywhere. They snap into these very specific groups, revealing this hidden order in the cosmos.
The first thing that jumps out is this huge band that cuts right across the diagram, from the hot, bright stars in the upper left down to the cool, dim ones in the lower right. This is the main sequence. About 90% of all stars, including our sun, spend the bulk of their lives right here, just steadily doing their thing, fusing hydrogen into helium.
But what about the other guys? Well, up in the top right, you've got the giants and supergiants. They're cool, so they're reddish, but they are incredibly bright. The only way that works is if they're enormous.
And then way down in the bottom left, you have the white dwarfs. They're super hot but really dim, which tells us they must be tiny, about the size of Earth. These are the embers of stars that have reached the end of their lives.
So, you see, the HR diagram isn't just a stellar census. It's more like a roadmap of a star's entire life. It lets us understand how they're born, how they live, and how they die. We can literally read their lifespan on this chart.
And here is the absolute crucial insight. What decides where a star gets to live on that main sequence? Is it some complicated mix of factors? Nope. It all comes down to one single thing: its mass. A star's mass dictates its temperature, its brightness, its color, literally everything. For a star, mass is destiny. And wow, does that destiny change depending on mass? The high-mass stars are the rock stars. They're luminous, they're blue, they're hot. But they burn through their fuel at an insane rate and live for only a few million years. The low-mass stars are the opposite. They're dim, red, and cool, and they sip their fuel so slowly they can last for billions, even trillions of years.
It gets even cooler. We can use all this to tell time on a cosmic scale. When we plot all the stars in a big cluster on an HR diagram, we can see exactly where the most massive stars are just starting to run out of fuel and turn off the main sequence. That turn-off point acts like a cosmic clock, telling us the age of the entire cluster. It's genius.
And when we use this technique on the oldest star collections we know of, these things called globular clusters, we find that they're about 13 billion years old. Which, by the way, gives us an amazing reality check on the age of the entire universe itself. We went from just points of light to the history of the cosmos.
So let's bring it all home with this one central idea. When you look at a normal star doing its thing on the main sequence, just remember, its mass is the key. Mass sets the rules. It determines everything we can see about that star.
Which brings us back home, to our star. The Sun is a G2V star. That V just means it's a stable main sequence star, right in the prime of its life. We've just learned how to decode the light from the stars, how to read their stories. We can read the Sun's current chapter pretty well, but now that we have the tools, it begs an even bigger question. What does its final chapter look like? What happens next? Well, that's a story for another time.